In a world where technology is advancing at an unprecedented rate, there is one buzzword that has caught the attention of everybody: quantum. From quantum computers to quantum cryptography, these quantum technologies have sparked a wave of excitement and promise to reshape the very fabric of our digital landscape. But what lies behind this hype? Are we really on a cusp of a quantum revolution, or are we simply caught in a whirlpool of excitement? In this video, we're going to separate facts from fiction for three of the most hyped quantum technologies: quantum computers, quantum cryptography, and quantum teleportation. So let's first talk about quantum computers. So quantum computers have gained a lot of popularity and garnered a lot of hype in recent years. They're widely discussed on the internet because of their potential capabilities and applications. We have often encounter claims such as quantum computers will be able to solve all our problems. They will be able to solve all computational problems. They will be infinitely faster than classical computers. They will be able to break the internet. So all our passwords, all the messages that we share, and all our information will no longer be secure. They will be exposed, and quantum computers will soon replace all classical computers at our homes. And some people even claim that quantum computers will be able to solve problems such as cancer. So is that really true? So now we're going to see what are the applications that quantum computers will be actually good at, what are the problems they will be actually able to solve, and what is just pure hype. So before we jump into the applications of quantum computers, I'm going to give a very short explanation on two key scientific ideas behind quantum computers and how quantum computer uses them: the idea of superposition and interference. But don't worry, don't just run away. You absolutely do not need to know any mathematics or physics to understand them. So, in a classical digital computer, the fundamental unit of information is a bit. And a bit is kind of like a switch. It can either be in the state off or in the state on. It can be in state 0 or in the state 1. But in a quantum computer, the fundamental unit of information is a qubit. And a qubit can not only be in the state 0 or 1, but also in some other states known as superposition. What is a superposition? So imagine a qubit is in a superposition state. Before we make the measurement, before we observe the qubit, or before we see the qubit, we have some probability to find it in the state 0 and some probability to find it in the state 1. So what does it mean? So imagine asking your boss for a raise or a promotion. So before you ask the boss, maybe the boss has not even thought about giving you a raise or a promotion. He has not thought about whether you should get a promotion or a raise. So, and when you do ask the boss, you have some probability to get a yes or get promoted or get a raise, and some probability to get rejected or get a no. Quantum computer uses superposition to solve problems. So a quantum computer uses multiple qubits in superposition to try different computation paths or different ways to solve a problem in parallel. So where a classical digital computer will try different ways to solve a problem or different computation paths one by one, a quantum computer, on the other hand, will try these different computation paths or different ways to solve a problem at once. So, but this is not enough to get the quantum speed up we hope to get. This is where the concept of interference comes into play. This interference. So imagine you're sitting on a beach enjoying your vacation and you see two waves coming together and interacting. So sometimes the two waves merge together and create an amplified wave, and sometimes the two waves cancel each other. Similar to waves, quantum superposition also have this property of interference. So how does quantum computer uses this to achieve speed up? So when the qubits in superposition perform the computation, the quantum computer uses interference to amplify correct answers and cancel out unfavorable or incorrect ones. So using this, we can actually achieve answers exponentially faster than classical computers. Take some myths. Myth number one: a quantum computer will be infinitely faster than a classical computer at everything. No, it's not true. In fact, it does not even make sense to say if something is infinitely faster. Infinity is not even a number. So the truth is, a quantum computer will be exponentially faster than a classical computer only for certain types of problems. So what does it mean? So so as the size of the problem increases, a quantum computer will be increasingly faster at solving it than a classical computer. So, and why only for certain types of problems? Well, because the concept of interference that we talked about can only be applied only for certain types of problems. Myth number two: quantum computers will replace classical computers. No, the truth is, for most of our computing needs, a classical computer will still be far more efficient than a quantum computer. Myth number three: quantum computers will solve problems such as cancer. This is also not true. A quantum computer is not magic. They will not just automatically solve problems like cancer. I mean, they may help us in some data crunching and stuff like that in research, but they definitely will not solve the problem just by magically outputting some cure. So, alright, enough with the bad news. What are the things that quantum computers will be good at? Number one, factorization. So, what are the implications for quantum computers being exponentially faster at factorization? Well, our modern security systems that protect our information from thieves on the internet is based on the fact that factorizing very large numbers takes years, even for hundreds of super fast classical computers. But quantum computers can, in theory, factorize large numbers very quickly and break the internet. And they can only do so if we are able to build full-fledged quantum computers with a large number of qubits, and which is very hard to do. And there are some other things such as solving linear equations that can be helpful in AI. We can also simulate nature very efficiently with a quantum computer. This can help us in improving energy efficiency, designing new materials in drugs, testing hypotheses, etc. And all this is possible only if we are able to build large-scale quantum computers with a lot of qubits. But it is actually very hard to do so. Companies and governments around the world are racing to build quantum computers, and very slowly we are actually making progress. So now let's talk about quantum teleportation. So this, along with quantum computers, also get people very excited. And teleportation has been a popular concept in fiction, captivating audiences with its ability to instantly transport people or objects from one place to another. People talk about how quantum teleportation could transport physical objects, including humans, from one place to another instantly. It can send messages instantaneously from one place to another place. But is that all really true? So before we talk about whether these applications are true or not, let's very quickly learn how quantum teleportation actually work. So the key concept behind the workings of quantum teleportation is the concept of entanglement. So what is entanglement? So when two qubits get connected in a way that their behaviors are linked together, no matter how far they are from each other, we call it an entanglement. So when two qubits become entangled, what happens is that when we measure one qubit, the qubit acquires a state. But the weird thing is that the other qubit also instantaneously acquires a particular state depending on the type of entanglement. So to make this idea more clear, imagine we have a pair of synchronized dancers who always move in a perfect harmony. So no matter how far apart they are from each other on the dance floor, when one dancer rotates in one way, the other dancer automatically rotates in the opposite direction. So their movements are linked and they can instantly respond to each other's actions even at a distance. So in quantum teleportation, the status or state of one qubit is transferred to another qubit. So how does this work? This is done by sharing a pair of entangled qubits between the sender and receiver. And by performing some measurements on qubits and sending some information about the outcome of the measurement to the receiver, we can transfer the state of one qubit to another. So okay, now we understand how quantum teleportation works. But let's break some myths about quantum teleportation. Myth number one, quantum teleportation can transport physical objects. No. See, the thing is, physical objects have extremely large number of atoms. And to transfer the state of each atom, we would need that many pairs of entangled qubits. And since there will be so many qubits, you can imagine how difficult it would be to keep track of each individual qubit. And remember, we would also need to transfer some information about our measurements on all those qubits via classical bits that can't transport information or transfer information faster than the speed of light. So it would take an extremely long time even with the fastest available internal connection. So it's not practical at all. Myth number two, quantum teleportation can transfer information faster than the speed of light. Not true as well. And for the same reason we already discussed before. Quantum teleportation requires sending some information through a classical channel that cannot send information faster than the speed of light. So okay, what is quantum teleportation actually useful for? Well, to be honest, their applications are not very exciting, at least to a non-technical person. So their applications include quantum secured communication, building quantum sensors, etc. But I'm not going to bore you with their details now. So we already talked about how quantum computers can crack the security system or encryption system that protects our information over the internet. So is there a security system or encryption system that can make our information safe forever from every possible attack? quantum cryptography promises to deliver just that. So let's once again see if the hype about quantum cryptography is really true or not. So first, let's just quickly understand some terms. Cryptography. The term cryptography just refers to the practice of protecting information from strangers by changing it into a form that is difficult to understand for an unauthorized person. So the next term we need to understand is a key. So any cryptographic system requires a key, and a key is required to encrypt the information or log the information and decrypt the information or unlock the information. So let us see what is the problem with our current most widely used cryptography system. Our current cryptography system involves two keys, a public key and a private key. The public key to log the message and private key to unlock the message. The public key is broadcast publicly so that the people who want to send a message to a person can log their message using the public key. And the private key is kept privately with the receiver so that he can unlock it. But there exists a way to find out the private key from the public key by doing some calculations. But this process takes a very long time. Hence, it makes a message secret for a long time, at least for now. But we already know if we build a quantum computer, a large scale quantum computer, then this system of protecting our information will no longer be safe. So a quantum cryptography system promises to share a private key between two people in a way that makes it impossible for anyone ever to find out what the key is. And this private key can be used to both encrypt the message and decrypt the message. So now let us understand how all this works. So first, the sender will choose a random sequence of zeros and ones or random sequence of bits and encode those zeros and ones into qubits in a superposition. And the sender can encode those zeros and ones in one of two ways and then send those qubits to the receiver. Then the receiver can perform measurements on the qubits to find out the outcome or the bits. And the receiver can perform measurements in again one of two ways. After measurement, the sender and receiver can just exchange with each other the information about their choice of measurement or encoding. For the qubits on which the receiver makes the same type of measurement in which the sender encoded it, the outcome of those qubits will be kept as private key. Isn't that amazing? But what if someone tries to find out the key when the qubits are on their way to the receiver? This is where the no cloning theorem of quantum mechanics comes into play, which simply states that a qubit can never be cloned. So if someone tries to measure the qubit, then their measurement will disturb the qubit, and then this disturbance can be easily detected by the sender and receiver. And this technology has already been commercialized, which makes it the most developed and promising quantum technology out there. But there are some problems. The qubits can be easily disturbed, which makes it not possible to share keys over longer distances using traditional fiber cables. And there are some other problems too, such as the devices used in this technology needs to be trusted. But this technology is still very promising. Researchers are working towards finding ways to fix these problems.